The familiar picture we have for integration of functions of a single variable is that having a function of a single variable, f of x, this can associate a height y over each base point x in the domain. And if it's a nice, smooth, continuous function, you get a nice, smooth, continuous graph. And we can do things like integrate. We can form integrals where we integrate from a to b f of x dx. Okay. This has an interpretation as the area between the curve and the x-axis between those 2 points. Okay, familiar with that idea? Okay, so it's the signed area between the graph of the function and the x-axis. Signed area because when the graph is positive, the area is counted positively in the integral, and when the graph is negative, when it creeps below the line, the area between it and the x-axis is counted negatively. Well, there is a similar construct or a similar type of integration you can do for functions of two variables. But before, in the one variable case, we were integrating over a interval of real numbers between a and b. Okay, so some sub-interval of the whole domain, the whole real numbers, which was the domain of the function. Whereas the appropriate thing here is going to be maybe some region. We're going to have some region R. So R is a region, a subset of the xy plane. And we are going to, instead, rather than talking about the area caught between the graph of a one variable function and the x-axis, we are going to be talking about the volume that lies over, see this region, if you project this region upwards onto the surface, it'll have some projection up onto the surface. And you can just draw a few lines suggesting what's going on here. There's going to be a certain volume trapped or bounded by the surface on the top of the volume, the xy plane at the bottom, and the kind of vertical projection of this region that we're integrating over upwards till it intersects the surface. Okay, so this volume here is going to be given by this kind of an object, where we're going to do a double integral of the function f of xy dx dy. Now we'll explain. We'll go through these things carefully and slowly. We'll explain what they mean and how to calculate them, but just to show kind of how they're arising. So this is going to be the volume of the cylindrical, and it's not an exact cylinder, but it's analogous to a cylinder, the cylindrical part of R3 bounded by the xy plane, which is the domain of the function. So just as in the one variable case, we looked at the area bounded on one side by the domain of the function, by the x-axis. Well, here the domain of the function is the whole of the xy plane. So it's the cylindrical part of R3 bounded by the xy plane on the bottom, the surface, z equals f of xy, and the vertical walls, if you like, over the region R. So this is the analogous thing to the integration of a function of a single variable over an interval a to b. We'll going to integrate our function of two variables over a region, a sub-region of the domain R, bounded below by the xy plane, above by the surface, and at the sides by just the vertical projection of that region parallel to the z-axis. Okay. So that's going to be one type of integral we look at, but there are other kinds of integral that we can talk about. We could also consider curves C in the domain of the function. These curves might go from a starting point A to an endpoint B. And we'll also look at things which are the integral over the curve C. This is a different kind of integral, not integrating. There's two integral signs here, not integrating over a two-dimensional subregion of the domain, but instead just integrating along a one-dimensional curve in the domain. We just use a single integration sign for that. But here we'll be integrating objects that look like, in general, a function of the two variables x and y dx plus another function, what have I called it, k, another function k of the two variables x and y dy. Now this thing doesn't have an immediate easy geometrical interpretation, but this is called the kind of path integral. It's the path integral of this object here, this h dx plus k dy, just suppressing the x and y arguments to h and k, just for writing it out there. So it's the path integral of h dx plus k dy over the curve C. So these are known as curve integrals of linear differential forms. These things, h dx plus k dy, these are known as linear differential forms. And that's another kind of integral that we're going to do. So this is all just looking ahead, just kind of drawing some pictures and naming some objects that we're going to see. If we come back to there's a link between these two types of integrals that we're going to talk about. See, any region like this in the plane is going to have a boundary. So there's going to be a closed curve, which is the boundary of the region R. So let's say this curve D, this is the boundary curve of R. So R was this two-dimensional region of the plane. D is the boundary curve. It goes around the outside of it. So we'll join the two types of integral together when we prove, or we're going to give a fairly detailed proof of it. I'm going to prove something called Green's theorem, which links the two types of integrals. And Green's theorem basically says that the integral of something dx dy is equal to the path integral over d of something dx plus something dy. Now, you can scroll forward a few pages and look at what the somethings are. But for now, just to get a taste of the kind of thing we're going to be doing, is that integrating a certain function along the boundary curve. So when you have one of these objects integrating a certain type of linear differential form along the boundary curve, under certain circumstances, we're going to be able to relate it to, it's going to be equal to, an integral of the first type, a double integral, over the region bounded by that curve. Okay? And the specifics of what the somethings are and what the conditions are we'll come to. But that's going to be where the integration section kind of culminates in drawing a strong link between these two types of integral that we have. So this thing is the 1D version. The 1D version of this. Okay, so this is the familiar thing we have from single variable calculus, and this is going to extend to something which plays a similar role, but now in the one dimension greater, where you got a function of two variables defining a surface. Okay, so this is going to occupy us for the next few lectures, and then we'll have finished the multivariable calculus section of the unit, and then we'll be going on to the second third of the unit, which is about Laplace transforms, okay, and the solution of certain kinds of ODEs. Okay, so that's some pictures and some names to get us started. But now we're going to look at these kind of integrals over here in a bit of detail. Okay, now it's unfortunate they don't have as nice a geometric interpretation as these so-called double integrals, but we'll be meeting these soon. Okay, so let's just have a look at these half integrals first. Okay, so this is section 1.11. Called in the notes line integrals, but variously they can be called path integrals or curve integrals. Integrals along a path, integrals along a curve, integrals along a line. They can all variously refer to the similar thing. Okay, so an object like this, which is a combination of the differentials dx and dy, okay, multiplied by two functions of the two variables x and y, this is called a linear differential form. A linear differential form in x and y. Okay. And these are the kind of things that we're going to be integrating. So this kind of thing here, we can sometimes suppress the x and y in brackets after the p and q. It's understood that p and q are functions relying on x and y. And this kind of thing is the integral of L along the curve C, where C is a curve in the plane. C is a curve in the xy plane, which is the domain of these functions p and q. Oh, sorry, my second thing here must be a dy. Sorry. Okay, so these integrals are a kind of a summation of the values of the linear differential form. They're an accumulation of all the values of the differential form that it takes along the curve C, where the p gets kind of triggered and accumulated as the x variable changes, and the q gets kind of triggered or accumulated as the y variable changes. Okay. But from a practical point of view, these can be evaluated, computed or evaluated by using features of C to convert the integral to a standard integral of a single variable function, something that we're already very familiar with from, from our first year calculus. So we're going to use features of the curve to convert the integral to a integral of a single variable function. Okay, something that we're familiar with from our earlier studies. Okay, so we'll have a look at the first example of one of these in example 14. So we'll integrate here. We're going to integrate this linear differential form L, which is 10 x squared y dx plus 3x plus 2 dy. And we're going to integrate this along a certain curve, along the curve C. And this curve goes from the origin to the point 1, 1 along the path y equals x squared. Okay, so in the domain of this function, we've got the origin, we've got the point 1, 1, and we're going along this path C. The path is described as the path y equals x squared. Okay, so the integral we're faced with is this integral I, which is the integral along C, 10x squared y dx plus 3x plus 2 dy. And so at the moment, this integral, as it's written, it depends on x and y. It features both of the variables. But we can use the specification of the path to convert the whole thing so that it only mentions one of the variables. Now, the way it's set up as it is, the natural thing to do would be to convert everything into x, okay? Because this specification of the path is telling you that you can replace y with the quantity x squared. Okay? So we would convert everything to the equivalent expression involving x. Okay? So that would mean we're integrating along the curve C. So first of all, we can just simply substitute in this expression here, substitute for y the quantity x squared. So what we're looking at here is actually 10x to the power 4 dx. And what we're looking at here is, well, it's still 3x plus 2. But now we were looking at the differential dy. But of course, if y is equal to x squared, then we can apply a kind of chain rule to work out what the relationship between the differentials dy and dx is. Okay. And dy is actually going to be 2 times x dx. Okay, so just taking the differential of each side, we get dy is equal to, well, okay, the differential of x squared, but we can apply the chain rule to say the differential of x squared is 2 times x, and then times the differential of the x. Okay. So then you get by 2x dx. So now this is good because we've converted our linear differential form, which was something featuring the two variables x and y. We've now converted it to just an expression in the variable x. Okay, so it's looking like just a familiar integral with respect to the x variable. And if you multiply this expression out, we can write it like this. So it's 10x to the power 4 plus 6x squared plus 4x. And then we can just put a single dx at the end. And the integral sign and the dx kind of act like a pair of brackets. So now this is supposed to be along the curve C, but rather than just putting down C again, because we've converted everything to the x variable, we can now look at the path C just in terms of the x variable. And what's happening to the x variable as you move along the path C, beginning at the origin, going to the point 1, 1? Well, the x variable is simply changing from 0 to 1. Okay? So our actual integral becomes this much more familiar, simple kind of integral. Just the integral from 0 to 1, 10x to the power 4 plus 6x squared plus 4x.
Why did you make it 0 to 1?
I just realized I took down the question slightly wrongly. There should be a y here. It doesn't matter too much, so I'm just putting in a y here, and that y should have been replaced by x squared. So this should be 2x squared there. So that makes this 4x cubed. Sorry, I just missed. I transcribed it slightly incorrectly from the notes. There should be a 2y here. So replace that y by x squared. It becomes a 2x squared there. 2x squared there. So it ends up being a 4x cubed. So apologies for that. Yeah, now we're good. So that finishes the translation part of the process. The specification of the curve is now built into this expression that we have, okay? This expression came from the original linear differential form, but we've substituted in the relationship y equals x squared. So although we seem to only be looking at the behavior of the x variable here along the curve C, begins at 0 and it goes to 1, we've actually built in the specification of the curve, the actual curve we're integrating along C, into the expression here. Okay, so everything is now in terms of the x variable, and this thing can just be integrated as you would have done, just as the type of integration that you're familiar with. Okay, so integrating 10x to the power 5, that's the integral of, 10x to the power 4, it's the integral of 2 times x to the power 5. This is plus 2x cubed and plus x to the power 4. And those get evaluated at the limits 0 and 1 for x. So substituting x equals 1, we get 5. We get 0 when we substitute in x equals 0, because they're all x's. So this gives us the final answer of 5, so to speak, for this integral. So that's an example of integrating one of these linear differential forms. And we'll do another example very shortly. But first of all, we'll have a look at Theorem 1.4, which just gives us some properties of these kinds of integrals that we can use, that we need to be aware about and we can use in our dealings with them. And they are all, they can all be viewed as generalizations of similar properties that you already know about for single variable integrals. Okay. Okay, so the first of these is that these operations are linear. So line integrals are linear. Now you're studying linear algebra with Stephen at the moment, so, and you're familiar with this idea from your study of integrals up to now. But if we are integrating along a curve C two linear differential forms, we can split that up as the integral of one of them plus the integral of the other one. Okay. So when your linear differential form is itself a linear combination of two other ones, the process is linear. You can integrate the first one and then add it to the integral of the second one. Or like it's written in the notes, you can integrate your linear differential form p dx plus q dy over curve C as just first the integral of the first one over C, and then plus the integral of q dy over the curve C as well. And of course, remember, from the single variable case, if you were faced with an integral from a to b of a function f1 of x plus f2 of x dx, I mean, you can split that into the integral from a to b of f1 of x dx plus the integral from a to b of f2 of x dx. Okay. This is saying that the integral of functions of one variable is a linear operation. And indeed, if you had scalars alpha and beta here, these scalars could move outside the integral sign as well. Yeah, I was forgetting about the presence of scalars. You can stick in the scalars here as well. So if you have scalars alpha and beta involved in this linear combination, they could move outside the integrations. So integration, as we knew it already in the single variable case, was a nice linear operator, and it still is, because now that we're looking at integrals of functions of two variables. Secondly, and I'll put the thing you're familiar with here first, if you had to integrate a function of a single variable f of x dx from a to b, you're familiar with that if you reverse the direction of integration, then you reverse the sign of the integral. So the integral from a to b of f of x dx is equal to the negative of the integral from b to a of f of x dx. Okay. So reversing direction is changing the sign. And we have exactly the same property. We have exactly the same property for these new kind of integrals we're looking at. So this is reversing direction is changing the sign. We've got exactly the same property, but now we talk about the integral along a curve C of linear differential form is the negative of the integral of the linear differential form along, let's say, C prime. So C is a certain curve in the xy plane from A to B. This is our curve C. The curve C prime is exactly the same curve, but traversed in the opposite direction. So the same A, the same B, the same curve between them. That's supposed to be exactly the same curve, but this time going in the opposite direction. Same path, opposite directions. Okay. Here, integrating from A to B is starting at A and ending at B. Integrating from B to A is just going in the opposite direction, starting at B and going along the x-axis to A. Well, we got the exact same thing, the equivalent thing in our integration of linear differential forms. And lastly, thirdly, we can subdivide our paths of integration. So again, the thing you're familiar with, I'll put in the bubble here. You've got an A, these intermediate ones, an A and a B and a C. The thing you're familiar with is that the integral from A to C of f of x dx, if you wanted to, if you're minded to, you can split that up as the integral from A to B of f of x dx plus the integral from B on to C of f of x dx. Okay, if you want to integrate a function all the way from A to C, you can first integrate it from A to B, and then secondly, integrate it from B to C. Okay, so this is subdividing the interval of integration, or dividing the interval of integration into subintervals. Well, we can do exactly the same thing with our linear differential forms. Okay, except this time we've got to imagine 3 points, A, B, and C in the plane, and we've got some curve that's going between them. But if you've got an intermediate point along the curve, then you can naturally split the whole curve up into C1 and C2. Excuse me. Where C1 takes you from A to B, and C2. So C1 is the curve A to B. C2 is the curve B to C. And C will take to be equal to C1 plus C2, which means the curve from A to C via B in the middle of it. But just the whole technical term is the concatenation of the two curves. To concatenate the two things is to run them end to end, one after the other. Concatenation. Just putting them one after the other. So what it says is that the integral of C of a linear differential form is equal to the integral of the linear differential form over C1 plus the integral of the linear differential form over C2. Okay. So it's not quite the linearity. It looks kind of like the linearity property we had before, but it's to do with subdividing. Well, the single variable case was subdividing the interval of integration. Here, for the two-dimensional linear differential forms, it's subdividing the path of integration. You're still traversing the same set of points. You're still traversing the same path. In the first case, you're just traversing it in one go. In the second one, you're first of all going from A to B, evaluating that, and then separately from B on to C, and evaluating that. So the next example shows us how we can make use of some of these properties, and it also shows up another feature that we're going to encounter. So this is example 15, where we're actually going to take the same linear differential form as we took before. I've included my y this time. And we're going to use the same ending and starting points. Sorry, go on.
Thank you.
We're going to integrate this along, or integrate this from the origin, which we'll call A, to the endpoint B, which is point 1 and 1. So it's the same starting and end points. The same starting and end points but this is the curve consisting of straight line segments. Straight line segments A to D and D to B, where D is the point 1, 0. So the picture for this path is we're starting at the origin A, we're going to the point B, but we're going in two straight line segments via this point D. So we're going along this path here, along the x-axis, and then up along here. Whereas before, remember, we went along the curve y equals x squared, which was this curve. That was when we did the integral before. So we're going to the same start point, same end point, but along a different curve. Now you see our curve here is it's very natural, of course, to split our curve up into two subcurves. Okay? Because the bit of the curve that goes from A to D is this curve, and that's quite different from the bit of the curve that goes from D to B. So it's extremely natural to split this up at the point B. So the integral from A all the way to B of this linear differential form, 10x squared y dx plus 3x plus 2y dy, it's natural to split it up into the bit from A to D plus the bit from D to B. And evaluate each one separately. Now in the first one, when you're on the curve from A to D, what's going on here? Well, x is starting from 0 and going to 1. Y is always fixed at the value 0. And because y is a fixed constant value, that means that the differential dy is also 0, okay? Because y is held fixed at a constant value. So the differential dy is 0, because y isn't changing. Whereas on the curve D to B, this vertical straight line segment, the situations are reversed. Here, y is going from 0 to 1. X is fixed at the value 1, and so again, dx is 0. Okay, because y is a fixed constant value on this portion of the curve. So we've got nice, straightforward behavior of the variables x and y on the two parts of the curve. And this is what allows us to do the evaluation. So continuing my equation here at the integral, on the first one, dy is 0, so I can completely ignore the second part. And y is fixed at 0, so actually I'm just integrating 0 dx from x equals 0 to x equals 1. That's just going to give me 0. So this was the A to D bit. Because dy is 0, so that cuts out all of that. And y is 0, so that actually cuts out all of that. So I'm just integrating 0 dx from 0 to 1. The second part of the integral, the dx is 0. So this first term in L, in the linear differential form, I can ignore, because dx is 0. The second one I have to evaluate. Y is going from 0 to 1, but x is always fixed at 1. So this 3x quantity here is actually just a 3, okay, because x is fixed at 1. So there I'm just integrating 3 plus 2y dy and y is going from 0 to 1. So that bit is the a to d. This bit is the d to b. So the a to d bit is 0, and the other bit integrates to 3y plus y squared, 0 to 1. And when you do those evaluations, you get simply 4. But the 4 is not the same as the 5 that we got previously. In the first example a few minutes ago, we integrated the same linear differential form from a to b, but along this curve, along the curve y equals x squared, and we got the answer 5. Okay. So what this example shows is this shows the typical behavior that such integrals depend on the path taken. Even though the start and end points might be the same. Okay. In general, we'd expect such integrals to give different values because they're moving through different points. Okay? So if the curves are taking you through different points, you're summing up or accumulating different values of the linear differential form, different values of the functions in the linear differential form. But there are special linear differential forms that are path independent. Where the values only depend on the starting and end points, and they're somehow special in that they don't really care about the curve you use as long as it starts and ends at the same point. So we'll be meeting these special linear differential forms later on, so we can look out for those. We'll encounter them later on. Okay, so that's enough for now, those first properties and the first few examples of our integrals. We'll do some more in this evening session at whatever time it is, 5 o'clock, I believe.